Greetings everyone. I'm a PhD student at Illinois Tech, Chicago. Today I will be talking about my work titled HCL Distributing Parallel Data Structures in Extreme Scale. HCL is a C++ data structure library that offers a library which is similar to the interface to STL. It supports asynchronous callbacks on data structures to support functionalities such as operation aggregation, filtering, collection, etc. It uses a novel RPC over RDMA protocol which enables efficient, highly programmable data structure framework. HCL builds upon PGAS model where it does not need any precompiler. It additionally extends PGAS model from using just a memory to persistent devices such as NVRAM and NVMe. As illustrated in this example, the green bar shows the shared memory space which is managed by HCL. The shared memory is a collection of several partitions which hold the data in this case, a key-value pair. Number of partitions can be less than the total number of processes, that is, it is possible to configure some of the processes to not hold any partitions. Data distribution within HCL is user-defined using a key space defined using std hash function. Additionally, for ordered datasets, the order is defined using std-less operator. As an illustrative example on the right, we can see the global virtual address space of an NR map is in reality divided into multiple partitions. A call within HCL can be local access within its own partition, an intra-node access to a partition within the same node, and inter-node access for accessing partitions in different nodes. HCL handles these three calls differently. For local and intra-node access, HCL uses shared memory model, and for inter-node access, HCL uses RPC call. This hybrid access model translates to performance benefits within HCL. The core principles of HCL are to enable RPC over RDMA protocol, where we get the benefits of RPC protocol such as ease of programmability, packing of instructions, etc., along with execution of instruction on the node core, which removes the RPC overhead on the target node. Event-driven design to allow executions of callbacks with data structure calls to allow complex high-performance functionalities which can take advantage of data locality. Hybrid data access model, as mentioned before, the differentiation factor of three types of calls with specific optimization allows HCL to extract maximum hardware performance. Finally, the persistent storage. The shared memory model with node can be extended to node local devices such as NVRAM and NVMe devices to extend the amount of space available to the global address space. Now we discuss how the RPC over RDMA protocol is designed. On the client side, a client stub is invoked by the client core, which serializes and calls RDMA send through the RDMA lib and waits for the response to be ready. On send, the RDMA request is sent to the queue to the target's receive queue. On arrival on the receive queue, the work queue framework running the NIC core pulls the request from the queue and decodes the message and executes the RPC call using the server stack on the NIC core, and then finally writes the response to the response buffer. Once the response is written, the notification is sent to the client for send completion. On this, the client would use RDMA read to read the response from the target server. The following is achieved. The following protocol achieves the following. RDMA one-sided to execute data operations. The decoding and execution of RPC protocol happens on the NIC core. Hence, the application CPU on the target node is not used. Client pull model ensures the server does not wait for client to receive the response, hence it can serve more other client requests. To quantify the benefits of this protocol, we perform a study to profile the resources of the target machine, which executes the RPC protocol. As seen in this figure, the CPU utilization of HCL is 3x lower than PCL, which performs remote CAS operation. The remote CAS takes hold of the remote main core and other parallel operations need to wait. Hence, HCL achieves a higher efficiency on the CPU. As HCL allocates memory using shared memory, it, it is not allocated at the start but dynamically. Hence, the same memory usage for HCL reaches the peak memory usage based on when the application allocates this. Finally, in the right most figure, for network utilization, BCL for every operation performs multiple network calls, whereas HCL performs only one network call with three local calls. This reduces the amount of congestion within the network because of lower number of messages in the network and hence allows a larger aggregate instruction bandwidth to be, to be achieved. Hence, HCL achieves higher network utilization as well. Overall, RPC over RDMA is extremely efficient in utilizing the underlying hardware. In the next couple of slides, we will showcase how we could use the distributed data structure library within HCL. A simple sort example can showcase its simplicity and power. In this example, we initialize all processes with set data structure. This is not a collective call. However, for convenience by default, we make it collective. Users can disable it based on a parameter-driven constructor. Then each process iterates over its data and inserts the value into the distributed set. This distribution, this, this insertion distributes the data across all the partitions using std hash function and maintains order through key space distribution using std-less function. Finally, we can get our local partition stored data using the local function. This example shows how we can perform distributed sorting within HCL with just 4 lines of code. Another example is when we want to access and mutate local data partitions. In this example, we use an array which is distributed among 4 processes. We can get the size of the local partition using lsize, which is a shorthand for local.size function. Additionally, we can refer to the local object which acts as a proxy to the local partition operations and updates the value at specific indexes. This showcases how we have full access to the local partitions and can perform optimizations based on where we are accessing the data. We now want to showcase the difference in performance between internode accesses and internode accesses compared to BCL, which treats all non-local partition calls as remote. In the first top of in the first test on top, we perform insert and find operations on a partition on the same client node. As it can be seen, optimizing these accesses through shared memory gives close to memory performance of the node. For the second test, we choose a partition on another node. As it can be seen, RPC over RDMA outperforms the multiple folds of NPI one-sided operations from BCL, and we get a speed of up to 5x. In general, internode accesses in HCL are bound by memory performance, and internode accesses are close to network performance of the cluster. Additionally, we see a better saturation of bandwidth for bigger data within the operations as expected. This is an overview of some of the data structures which are supported within HCL. As it can be seen, map and set data structures support insert and find operations, and queue supports push and pop operations. These data structures are analogous to SQL data structures within C++. We then showcase the performance of each data structure compared to the state-of-the-art data structure library. In this case, the HCL data structures outperform BCL in almost all cases. Additionally, we see maintaining order within data structure reduces the performance of HCL by 20 to 40% in certain cases. This is due to the ordering is a login operation, which reduces the overall performance of the data structure. Finally, we showcase the use of HCL data structure within three real workloads and show how it can be used to enable 10x better performance as compared to the state-of-the-art solution. In conclusion, in this work we showcased a novel RPC over RDMA architecture. We designed and implemented STL-like data structures which can improve application performance by almost 12x. Thank you for listening to this talk. Please email me your comments and questions at the Q&A email ID. Thank you again.